Hello my friends and welcome back to the You Can Do TV channel. High above the skyline of Dubai, a defining moment in structural engineering was achieved with the completion of the Za'abeel Phase 2 link bridge lift. This extraordinary structure, set to become one of the world's longest occupied cantilevers, connects the twin towers while projecting dramatically into open air. The lift operation required meticulous planning and precision execution. The massive steel bridge section, weighing thousands of tons, was assembled at ground level before being hoisted in a synchronized heavy lift operation, using strand jacks and specialized lifting frames. Incremental lifting allowed engineers to carefully control deflection and alignment as the structure rose into position. Once elevated, the bridge was secured to the towers, forming a continuous load path capable of handling both structural forces and dynamic loads. Temporary supports were then removed, leaving the cantilevered section suspended. This milestone highlights advanced construction sequencing, pushing the limits of high-rise engineering and redefining Dubai's architectural skyline. At Hinkley Point C in Somerset, a defining construction milestone unfolds as the world's largest crane, Big Carl, performs one of the project's most dramatic lifts. The massive steel dome for Unit 2, standing 14 meters tall and weighing 245 tons, is carefully hoisted into position atop the reactor building. Spanning 47 meters, wider than the dome of St. Paul's Cathedral, the structure contains more than 900 precision welds. Once installed, the dome seals the reactor building, allowing interior work to accelerate. With lessons learned from Unit 1, construction on Unit 2 is progressing significantly faster, paving the way for installation of the reactor and steam generators. High above the skyline of Taichung, Taiwan, a dramatic final chapter unfolds in the construction of the National Trade Center. As the structure nears completion, attention turns to the towering crane that once powered the project's rise. Removing it requires extraordinary precision. A Liebherr LG 1550 mobile lattice boom crane is deployed to dismantle the rooftop tower crane piece by piece. Positioned with careful planning, the heavy lift machine hoists massive components safely down to ground level. The operation marks a symbolic moment, signaling that one of Taichung's most prominent commercial landmarks is approaching completion. Deep beneath the massive construction site of Hinkley Point C, a critical engineering moment unfolds. A 230-ton triple-point shaft formwork is carefully lowered 40 meters underground to connect three major tunnels. Guided entirely by cameras due to tight tolerances and confined space, The precision lift navigates uneven shotcrete walls before settling into position. Once secured, vast volumes of concrete will lock the structure in place, forming a vital junction designed to support the nuclear power station for the next 60 to 80 years. Constructing a 500 kV high-voltage transmission line demands meticulous coordination, particularly during the installation of the heavy aluminum steel conductor within an anchoring span. The process begins with the deployment of a leader rope, which serves as the guiding line used to pull the final conductor across the towers. Crews first install stringing rollers onto the insulator strings at each intermediate tower. These rollers support the temporary passage of the rope and conductor, while preventing damage to the cable during installation. Using a tractor equipped with a winch, the leader rope is gradually pulled along the route and lifted onto each tower, passing smoothly through the mounted rollers. The rope is unreeled from drums and extended across the span, sometimes joined using special clamps to form a continuous pulling line. At the same time, braking machines are anchored on one end of the line, while hydraulic tension equipment controls the movement of conductor drums on the opposite side. Once the leader rope reaches the far anchor point, the main conductor is attached using a temporary pulling sock grip. As the rope is winched forward, the heavy conductor is carefully drawn across the towers through the stringing rollers. Sliding grounding devices are installed along the wire to ensure electrical safety during the operation. After the conductor reaches its final position, crews perform tensioning and anchoring, securing the cable to the tower hardware. The wire is then transferred from the temporary rollers into permanent suspension clamps connected to the insulator strings. Finally, protective spiral rods and spacer dampers are installed along the conductors using inspection trolleys, stabilizing the line against wind-induced vibrations and ensuring reliable long-term operation of the high-voltage transmission corridor. Deep within the protected wetlands of Troy Meadows in New Jersey, a complex power grid upgrade unfolds under unusual conditions. Stretching across nearly 3,000 acres of sensitive marshland, the transmission corridor can only be reached by a narrow service path known locally as the Green Mile. Heavy construction equipment cannot enter the area without damaging the fragile ecosystem, leaving only one viable solution: construction by helicopter. High above the marsh, Ericsson's powerful air crane helicopters carry steel tower components weighing more than 10 tons at a time. Flying with remarkable precision, pilots deliver each section of the monopole transmission towers directly to crews waiting below. On the ground, specialized teams quickly guide the pieces into position, securing bolts and connections as the structure gradually rises skyward. Months of planning go into every lift. Engineers and field crews coordinate closely with contractors to ensure each tower section is designed specifically for aerial installation. Every movement is choreographed in advance, while pilots and ground teams maintain constant radio communication to guide the suspended loads safely into place. The result is a carefully orchestrated aerial operation where machinery, engineering, and human expertise work in perfect synchronization. By day's end, towering steel structures stand firmly in place, modern transmission lines rising above an untouched wetland, ready to deliver reliable electricity to thousands of homes. High above the ground, a transmission line technician rides a specialized inspection trolley along massive high-voltage conductors. Suspended in open air, the worker installs spacer dampers between bundled cables, devices that maintain spacing and reduce destructive wind vibration. Every movement must be precise. At this height, strong winds, heavy equipment, and the proximity to powerful electrical currents create constant danger. Secured by safety harnesses and careful coordination, crews methodically tighten each unit, ensuring the transmission line remains stable and capable of delivering electricity safely across long distances. Across the immense landscapes of Brazil, an engineering corridor stretches for thousands of kilometers, carrying electricity from remote hydroelectric plants toward the country's largest cities. Building such an ultra-high voltage line required massive steel lattice towers designed to support heavy bundled conductors and withstand strong wind loads across open terrain. Construction crews first installed deep reinforced foundations before assembling tower sections using cranes and specialized lifting equipment. Once the towers were completed, the most delicate stage began: conductor stringing. Leader ropes were pulled through stringing rollers mounted on each tower, allowing the massive aluminum steel cables to be gradually drawn across long spans using tensioners and braking machines. Precise control of tension ensured the conductors maintained the correct sag and clearance above the ground. After installation, the cables were transferred from temporary rollers into permanent suspension clamps attached to the insulator strings. Spacer dampers were then installed between bundled conductors to control vibration and maintain stable spacing. The finished line now forms a crucial artery in Brazil's energy network, transmitting large volumes of hydroelectric power across vast distances with remarkable efficiency. Inside a highly controlled production environment, the manufacturing of glass insulators unfolds as a precise sequence of forming, tempering, and rigorous testing. The process begins with fully automated feeding into an electric kiln furnace, where molten glass is shaped using high-pressure press machines. From there, components pass through soaking kilns and tempering systems, followed by thermal shock lines that enhance mechanical strength and resistance to extreme conditions. Each semi-finished unit undergoes visual inspection before moving to assembly, where adhesive preparation, cementing, and pin installation are completed with strict tolerances. Quality assurance is exhaustive. In dedicated laboratories, insulators are subjected to mechanical load tests, high-voltage breakdown tests, and lightning impulse simulations. Coating thickness and head pressure resistance are also verified. Only after passing every inspection stage are the insulators approved for packaging, ensuring long-term reliability in high-voltage transmission networks. Across a vast reservoir in Shandong Province, China, the Jinko 100 megawatts floating solar project demonstrates the rapid evolution of large-scale photovoltaic engineering. Thousands of solar panels are mounted on buoyant platforms that spread across the water's surface, transforming unused reservoir space into a powerful clean energy generator. The floating structures are interconnected and anchored to withstand wind, waves, and changing water levels. Electricity produced by the panels is transmitted through floating cables to an onshore substation. By using water surfaces instead of land, the project maximizes energy production while reducing land use pressure in densely developed regions. Along the windswept coast of Brest, France, a compact 25 kWp floating solar platform demonstrates a new frontier in renewable energy. Designed for harsh nearshore conditions, the system anchors to innovative moorings that rise and fall with 7-meter tides. Flexible floating cables safely transmit power, turning unused harbor waters into reliable, clean electricity. Across vast solar construction sites, a quiet technological shift is reshaping how photovoltaic farms are built. At the center of this transition is a robotic installation system powered by KUKA industrial robots, designed to accelerate the placement of heavy solar modules. Each photovoltaic panel can weigh 70 to 80 pounds, 32 to 36 kilograms, a load that quickly exhausts manual crews during long installation cycles. To address this challenge, engineers integrated a KUKA KR70 Iontech robotic arm onto a rugged autonomous ground vehicle. Guided by computer vision, the robot identifies the precise position and orientation of each module, lifts it using a custom suction gripper, and places it onto the mounting rack with millimeter-level accuracy. Built with foundry-grade protection, the robot operates in harsh outdoor environments, dust, temperature swings, and uneven terrain. Force torque sensors provide feedback while handling fragile glass panels, ensuring safe and consistent placement. The result is a faster, more repeatable installation process, reducing worker fatigue while enabling solar farms to scale construction at unprecedented speed. At the California Science Center, a historic piece of spaceflight engineering rises once again. ET-94, the last flight-qualified space shuttle external tank ever built, is carefully lifted and installed beside the towering solid rocket boosters. Weighing 65,000 pounds and stretching 154 feet tall, the massive orange tank forms the backbone of the shuttle stack. This dramatic operation is part of the complex go-for-stack process, assembling Space Shuttle Endeavour into the world's only authentic, ready-to-launch vertical display, an inspiring centerpiece for the future Samuel Oschin Air and Space Center. Engineering ambition defines the construction of the Samuel Oschin Air and Space Center in Los Angeles, where the full Space Shuttle Endeavour launch stack is being assembled for permanent display. The installation required an unprecedented structural and logistical strategy. Engineers position the orbiter together with its external tank and twin solid rocket boosters, recreating the exact launch configuration normally seen only at NASA facilities. Because the shuttle stack rises nearly 20 stories, the components had to be installed midway through building construction. Specialized lifting operations placed the massive elements onto a reinforced structural base designed to distribute the combined loads of the orbiter and boosters. Protective steel framing and temporary enclosures were erected around the stack to shield it, while the surrounding galleries continued to rise. The project adds roughly 200,000 square feet of exhibition space, integrating large aircraft displays and multi-level galleries around the shuttle structure. Precision engineering ensures the building envelope, structural supports, and viewing platforms align perfectly with the towering shuttle configuration. On major highway projects, achieving a perfectly uniform asphalt surface requires more than just laying hot mix. It demands precise coordination. One effective method is Echelon paving, where multiple pavers operate side by side. In this operation, 4 asphalt pavers work simultaneously to place a continuous mat across the full roadway width. The main goal is to eliminate cold joints, which form when hot asphalt meets a previously cooled edge. These joints create weak points that can lead to cracking, water intrusion, and premature pavement failure. By paving the entire width at once, the asphalt remains hot and fully bonded across the surface. Each operator controls a dedicated paver, while crews synchronize speed, material flow, and alignment. The result is a seamless asphalt layer, stronger, more durable, and far less prone to structural weakness over time. Along Brazil's 800 kV Xingu Terminal-Rio transmission corridor, one of the most demanding construction stages begins with the foundation works. At the Araguaia River crossing, massive transmission towers reaching 120 meters in height require exceptionally strong support. Engineers construct deep root pile foundations, drilling reinforced piles into the ground to anchor the structures against enormous mechanical and wind loads. These foundations stabilize the towers that will carry ultra-high voltage conductors across the wide river span, forming a critical section of the long-distance power link connecting northern hydroelectric generation to Brazil's national grid. On a fast-moving job site, precision defines the installation of large, precast concrete wall panels using the InnovaCast system. A high-capacity Innova telehandler lifts each panel directly from a specialized trailer, maneuvering the massive element into position with controlled reach and stability. Engineers and rigging crews guide the placement, ensuring alignment with embedded anchors and connection points. Every movement is coordinated to avoid stress on the panel while achieving tight tolerances. This method accelerates structural enclosure, reduces on-site casting, and delivers consistent quality, transforming large-scale building construction into a streamlined, highly controlled assembly process. Rising above the heart of the city, the Nairobi Expressway was rapidly taking shape, reaching approximately 45% completion just 9 months after launch. Construction advanced around the clock, with crews working 24 hours a day across key sections including Cabanas, Uhuru Highway, and Chiromo. The elevated corridor is engineered to dramatically transform mobility, cutting peak travel time across Nairobi from nearly 2 hours to just 20 minutes. Beyond transportation efficiency, the project is expected to generate hundreds of local jobs and strengthen Kenya's role as a critical link in the northern corridor for regional freight movement and tourism growth. Beneath the busy streets of Sydney, a massive engineering effort is quietly strengthening the city's electrical backbone. As part of the Powering Sydney's Future initiative, a complex 330 kV underground transmission system has been installed along a 20-kilometer route, requiring a total of 60 kilometers of high-voltage cable arranged in twin and single circuits. Construction unfolded through several carefully coordinated stages. The first involved extensive trenching operations, with 16 construction crews working simultaneously across multiple districts. The route crossed 3 local council areas and required specialized infrastructure, including bridge crossings and 16 horizontal directional bores to pass beneath roads and obstacles. Next came the installation of precast joint bays, critical underground chambers where cable sections connect. Cable pulling then began using enormous 48-ton cable drums, among the largest ever transported in Australia. A specially engineered rotating drum platform allowed these massive reels to be positioned safely on site. Winches pulled the cables through underground conduits, while mechanical caterpillar pushers assisted the movement along long pipe sections. Specialist technicians later completed precision cable jointing before final testing and commissioning. Completed in just 10 months, the system now forms a vital high-capacity energy link powering Sydney's growing urban network. Along the mineral-rich coastline of West Africa, the Republic of Guinea holds one of the world's most valuable geological treasures, bauxite, the essential ore used to produce aluminum. Vast deposits scattered across the country have positioned Guinea as the largest supplier of this strategic resource to global markets. Transforming that raw potential into a steady export stream, however, requires engineering on a massive industrial scale. At the heart of this effort stands a colossal bauxite handling facility built to support international aluminum production. Developed for Emirates Global Aluminium, the terminal moves ore from inland mines to the coast through an integrated network of wagons, conveyors, and port loading systems. Trains deliver freshly mined bauxite to a wagon tippler, where the ore is discharged and transferred onto a 6-kilometer conveyor system capable of transporting up to 4,000 tons per hour. Towering above the operation is the facility's most formidable machine, a 600-ton stacker reclaimer. Installed using 2 specialized 715-ton cranes, the giant mechanism organizes and retrieves stockpiled ore, eventually handling as much as 10,000 tons of bauxite per hour. Another critical component, a 415-ton car dumper, required careful relocation into its pit, using self-propelled modular transporters, allowing the enormous structure to move safely across uneven ground. Logistics posed its own challenges. Construction materials arrived from India, Dubai, and Europe, while more than 400 skilled workers were deployed alongside over 1,000 local employees. Despite the complexity, systems that typically require a year to complete were delivered in just 9 months. The result is more than an industrial installation. It is a gateway linking Guinea's vast mineral wealth to the global aluminum supply chain, reinforcing the nation's pivotal role in the world's resource economy. A new benchmark in trenching technology has been set with the MT4500 megatrencher. This colossal machine carves an extraordinary trench reaching 145 feet deep and 36 inches wide, pushing the limits of mechanical excavation. Even at such extreme depth, the system maintains a steady production rate of 6 inches per minute. Designed for large-scale infrastructure projects such as pipelines and utility corridors, the MT4500 demonstrates how modern trenching equipment transforms what once required months of drilling into a continuous, high-precision operation. Along long stretches of remote terrain, building the foundation of a border wall demanded a method that was both precise and continuous. The solution emerged in the form of the DeWind one-pass trenching system, a specialized machine designed to excavate and stabilize the foundation in a single operation. The customized trencher cuts a 6-foot wide trench approximately 8 feet deep, operating only 2 inches from the international boundary. As the cutting chain advances, native soil is simultaneously blended with Portland cement and water, creating a stabilized soil cement foundation directly within the trench. Tanker trucks supply water, while dry cement is pneumatically transferred into onboard hoppers and metered into the trench through vertical augers. Crew members guide the machine along precise alignment stakes to maintain the exact wall corridor. The continuous mixing process eliminates repeated excavation and backfilling cycles, allowing the foundation to be formed without interruption. After stabilization, the upper section is trimmed to create a level platform. A narrow key trench is then cut along the center line, preparing the base for the installation and concrete embedding of the permanent wall panels. Before a deep foundation can support a massive structure, the board pile head must be precisely prepared. After the pile is cast, the upper portion often contains weak or contaminated concrete from the drilling process. Workers therefore perform pile head hacking, carefully breaking away the top layer using pneumatic breakers or hydraulic tools. The goal is to expose clean, dense concrete and the reinforcement bars beneath. Once revealed, the steel rebar cage can be properly connected to the pile cap or foundation beam. This step demands precision. Removing too little leaves weak concrete, while excessive hacking risks damaging reinforcement. It is a small but critical operation that ensures the hidden strength of the entire structure. In confined urban corridors where precision matters as much as power, the KEMROCEK 140 emerges as a highly specialized solution for rock excavation. Mounted on an excavator, this chain cutter attachment is engineered to cut through hard materials such as rock, reinforced concrete, and asphalt with controlled accuracy. Unlike traditional breakers that generate vibration and noise, the EK140 uses a continuous cutting chain equipped with durable picks, allowing for low vibration, low noise trenching. This makes it ideal for sensitive environments, near existing structures, utilities, or dense infrastructure networks. The attachment excels in producing narrow, clean trenches with consistent depth and vertical walls, reducing the need for additional finishing work. Handling oversized plasterboard at height demands both control and adaptability. This is where the EDMA megaboard lifter stands out. Engineered for multi-position use, it supports horizontal ceiling installs, angled raked ceilings, and vertical wall placement with equal precision. Its robust frame allows lifting of sheets up to 6.0 meters long, reaching fixing heights of 4.5 meters, while safely handling loads up to 80 kilograms. A rack and pinion mechanism, assisted by a power drill, reduces operator effort and ensures smooth elevation. A key safety feature is the dual braking system, combining a main brake with a secondary safety brake for controlled descent. Adjustable arm extensions, height settings, and a stable wheeled base with lockable casters enhance versatility. Designed for demanding interiors, it transforms drywall installation into a safer, more efficient operation. Beneath the smooth curves of a custom swimming pool lies a construction method built on speed, strength, and precision. Shotcrete. The process begins with excavation and the installation of a carefully shaped reinforcement cage, defining the pool's geometry. Concrete is then pneumatically projected at high velocity through a hose, compacting instantly as it strikes the steel framework. This method eliminates the need for traditional formwork, allowing builders to create complex shapes with continuous structural integrity. Skilled nozzle operators control thickness and density, ensuring uniform coverage across walls and floors. Once applied, the shell cures into a dense, monolithic structure, ready for waterproofing and finishing, delivering durability and design flexibility in one seamless operation. Across the powerful currents of the Dardanelles Strait, constructing the 1915 Canacale Bridge required one of the most complex marine engineering operations ever attempted in bridge construction. Construction first focused on the massive tower foundations, built using enormous steel caissons. These hollow structures were fabricated on land, floated to position, and then carefully sunk onto the prepared seabed. Each caisson weighed tens of thousands of tons and had to be positioned with extreme accuracy despite strong currents and deep water conditions. Once aligned, the structures were filled with reinforced concrete to create stable bases capable of supporting the bridge's towering pylons. With foundations secured, engineers assembled the bridge towers segment by segment. Prefabricated steel tower blocks were transported by heavy lift barges and raised using giant floating cranes. Each section was bolted and welded in place while crews worked hundreds of meters above the sea. As the towers climbed higher, temporary stabilization systems ensured structural alignment and resistance against wind loads common in the strait. After the towers reached full height, construction moved to one of the most iconic phases of suspension bridge building: main cable spinning. Thousands of high-strength steel wires were pulled back and forth across the span, gradually forming the enormous suspension cables. These cables would ultimately carry the entire weight of the bridge deck while distributing loads evenly across the towers and anchor blocks. The bridge deck was assembled using massive prefabricated steel segments. Specialized heavy-lift vessels transported these sections beneath the cables, where lifting frames hoisted them into place one by one. Workers then secured each segment to the vertical suspender cables, gradually extending the roadway outward from both towers until the final closure at mid-span. Throughout construction, engineers had to coordinate operations over one of the world's busiest maritime routes. Strong winds, shifting currents, and seismic considerations required constant monitoring and adaptive engineering solutions. The result is a structure that not only connects Europe and Asia, but also showcases the extraordinary scale and coordination required to build the world's longest suspension bridge. Across parts of the Middle East and Africa, massive infrastructure programs are transforming coastlines, highways, and industrial zones. Among the contractors involved in these developments is EDEX, a firm that has participated in a range of technically demanding civil and marine construction projects. The work typically focuses on complex structural systems, where heavy lifting, deep foundations, and precise logistics must operate together. Many of these projects involve marine infrastructure, where construction takes place directly over water. Building quay walls, port terminals, and offshore structures require specialized marine equipment, such as floating cranes, pile-driving barges, and heavy transport vessels. Steel piles, or reinforced concrete piles, are driven deep into the seabed to create stable foundations capable of supporting massive loads from cargo operations and maritime traffic. Large infrastructure corridors represent another major area of activity. Highway networks, interchanges, and long-span bridges require extensive earthworks, ground stabilization, and reinforced concrete construction. Surveying teams establish exact alignments before foundation crews begin installing piles, footings, and structural supports. Once substructures are complete, large precast or steel bridge components are transported and lifted into position using high-capacity cranes. Transporting oversized components often becomes one of the most demanding logistical phases. Bridge girders, precast beams, or heavy mechanical equipment must be moved across unfinished terrain or congested urban zones. Self-propelled modular transporters and specialized lifting frames are frequently used to position these components safely and accurately. Such projects also involve the coordination of large workforces and multinational supply chains. Structural steel, heavy equipment, and specialized components are commonly sourced from different regions and delivered according to tightly controlled schedules. Detailed planning is necessary to keep excavation, foundation work, structural assembly, and finishing operations moving simultaneously. The scale of these developments highlights how modern civil engineering projects operate today, through careful sequencing of heavy machinery, large material flows, and coordinated engineering teams. The final structures, whether ports, bridges, or transportation corridors, often represent years of planning and construction carried out under demanding environmental and logistical conditions. Beneath the busy railway district of Pasila, Helsinki, an enormous underground construction effort unfolds to create the Tripla complex parking facility. At the heart of the project lies a massive RD pile retaining wall, engineered to stabilize the ground while excavation proceeds for the underground car park. Installation begins with the delivery of full-length steel piles, some reaching 3.5 meters in length. A vibratory hammer first drives the piles through the upper layers of clay and silt until they reach the denser moraine below. Once positioned, specialized augers remove the soft clay from inside the pile. The piles are then drilled deeper through the moraine and finally anchored approximately 1.5 meters into the bedrock, creating a stable structural barrier capable of resisting immense soil pressure. Working conditions are particularly demanding. Many piles must be installed beneath an active railway track, where the available headroom is only 6 meters. To operate within these restrictions, crews use shorter 4-meter pile segments, which are then splice-welded on site to form full-length RD 412.5 piles, measuring between 15 and 22 meters. After the retaining wall was completed, excavation for the underground car park removed nearly 640,000 cubic meters of material. Structural stability is further reinforced by an extensive anchoring system consisting of 808 anchors and nearly 20 kilometers of casing for RD 140 and RD 170 anchor piles. Construction continues with additional large-diameter RD 1200 piles supporting both the parking structure and the nearby Pasila station expansion, forming one of the largest underground developments in Finland. In West London, between Old Oak Common Station and the West Ruislip Portal, a massive underground structure forms a critical part of Britain's HS2 high-speed railway. Known as the Victoria Road Crossover Box, the facility serves 3 essential functions: launching tunnel boring machines, providing natural ventilation for the railway tunnels, and allowing trains to switch tracks in case of disruption. Construction began with major ground preparation. Existing made ground was removed and replaced with a 1.6-meter thick piling platform capable of supporting heavy machinery. Engineers then installed 77 tension piles, creating the deep foundation required to anchor the future base slab. The surrounding structure was built using diaphragm wall construction, where reinforced concrete panels were excavated and poured from ground level in about 70 individual sections. Large reinforcement cages, some requiring 100-ton lifts, were assembled on site and transported using a 128-wheel, self-propelled modular transporter. Excavation progressed in stages until the pit reached roughly 25 meters deep. The finished box measures 128 meters long and 42 meters wide, with around 240,000 tons of clay removed. Its optimized, caterpillar-shaped design reduces concrete use by nearly 40%, improving structural efficiency before tunnel boring machines begin their underground journey. Deep within Peru's mining sector, a remarkable engineering feat unfolded as Ferreiros completed a full reconstruction of the CAT 7495 electric rope shovel, a machine exceeding 300 tons and among the largest in Caterpillar's global fleet. After more than 100,000 operating hours, the shovel entered a meticulously planned overhaul designed to restore full production capability. The process began with a comprehensive disassembly phase, involving both on-site and workshop operations. Over 24,000 man-hours were invested across more than 4 months as teams dismantled massive structural components, including frames measuring 12 meters in length and weighing up to 60 tons, alongside critical assemblies reaching 90 tons. Each component underwent detailed inspection, repair, or replacement before reassembly. The boom, extending 21 meters and weighing approximately 70 tons, required precision lifting and alignment to meet strict tolerances. Structural integrity, mechanical systems, and electrical subsystems were all restored to operational standards. The reassembly phase demanded synchronized heavy lifting and exact sequencing, ensuring all elements integrated seamlessly. Notably, the entire operation was completed with a zero-accident safety record, underscoring disciplined execution. This reconstruction effectively delivered a second life to one of the mining industry's most powerful machines, extending its service horizon and reinforcing the value of advanced life-cycle engineering in large-scale mining operations. In rural electrification projects, efficiency often depends on smart equipment integration. The tractor-mounted concrete pole lifter with auger attachment combines two critical operations into a single system, lifting heavy RCC poles and drilling precise foundation pits. Powered by hydraulic controls, the auger bores consistent holes, while the lifting arm positions poles with stability and balance. This two-in-one configuration reduces manual handling, lowers labor demand, and accelerates installation cycles. Designed with robust steel fabrication, the system performs reliably across varied terrain, delivering a practical and cost-effective solution for power distribution infrastructure. In extreme winter operations, the Teamco Snowblast M9000HD delivers high-capacity snow removal through an advanced dual-fan system. Each fan integrates helical ribbon augers, eliminating the need for cross augers while maintaining continuous material flow. A telescoping discharge spout allows flexible operation, either loading trucks or casting snow at distance. All machine functions are managed via wireless remote control, enabling precise, safe operation from a distance in harsh, high-volume clearing environments.